Good afternoon, everyone. I'm sorry I couldn't be there with you today, but I'm hoping this recording will be enough to get you started until my return. So let's talk about polynomials, which is our new chapter that we're moving on to. So 6A, we're going to start with an overview, the language of polynomials. And we're looking at this kind of function here, which does look very complicated, but basically when we talk about polynomials, we're talking about something that has two or more terms, and they have different powers. So a quadratic would be an example of a polynomial. In this chapter, we will be looking at polynomials that have x to the power of 3 specifically, but we have been technically working with polynomials up until this point. Now, just a few terms to get us started. When we talk about the zero polynomial, the numbers, that's when we're talking about the number 0. The leading term is the first term. So the highest index, which means the highest number power, is going to be your leading term. So when we work with quadratics, our leading term is x squared. Now that we're working with cubics, our leading term is going to be x to the power of 3. The degree of the polynomial is the index or the power of the leading term. So again, with our quadratics, the degree of the polynomial is 2. With our cubics, the degree of our polynomial is going to be 3. The monic polynomial is a polynomial whose leading term has a coefficient of 1. And then the constant term has the index of 0. So remember, anything to the power of 0 is going to be equal to 1. Okay, now getting us started with the arithmetic of polynomials. Now we have seen this form quite a bit now, so I'm hoping this is going to jog your memory of our function notations. So we have our first polynomial here that is p of x, and then we are given a second polynomial that is q of x. Now, in question A, it wants us to add p of x and q of x. So all we're going to do is we have our p of x and q of x, and we're simply going to add them together. So I'm going to have x cubed minus 6x plus 3. And then I'm going to add, because we've got our addition here, plus x cubed minus 3x plus 1. And then we're going to add our like terms. So I've got 1x cubed here and no other x cubed. So that's going to remain as x cubed. My 6x, I can see that I've got a 3x matching, but I'm going to go in degree order, which means that I'm going to go down to my x squared now. So my x squared is going to come next. So when you're writing out your polynomials, try and write them with the degrees in order, so 3, 2, 1 for the powers. So next I'm going to go to my 6x and 3x because they have x to the power of 1, so they'd be next in line. So my negative 6x minus 3x is going to lead me to negative 9x. And then I have my two constants on the end here. So remember the constants, the x is to the power of 0, which makes it 1, which means we don't have an x with these terms. So 3 plus 1 is going to be 4. Moving over to B now. Now we have this minus in the middle, so please be mindful of that. So with our question B, I'm going to have my p of x again. So x cubed minus 6x plus 3. Now, this time I'm going to have the minus, so be mindful that you're going to do minus in brackets q of x. And so this is going to change all of the signs in our bracket. So it is important that you put it inside this bracket, because when I go to expand it out now, writing my p of x first, I'm going to have minus x squared. This minus and the negative 3x is going to turn to plus 3x. Negative times my positive 1 is going to be minus 1 on the end. So collecting our like terms again, I've got x cubed minus x squared, negative 6x plus 3x. I'm going to have negative 3x, and then 3 minus 1 is going to be plus 2. Now, had I not put these brackets in, I would have only had this negative x squared, and then the rest would have been a negative 3x and plus 1. So it is important to put it inside the brackets. Okay, now last but not least, we're multiplying with our part C, our p of x and q of x. So I've got x cubed minus 6x plus 3, and then multiplied by my x squared minus 3x plus 1. So just like multiplying any brackets, we're multiplying each of the terms together. So I'm going to have my x cubed times x squared, and then I'm going to do my x cubed again, multiplied by my next term, which is the negative 3x, and then x cubed plus 1, x cubed times 1, so just plus x cubed. Next, I'm moving over to the 6x, so minus 6x times x squared. Next, minus 6x times my next term of minus 3x, and then minus 6x times 1, and then lastly the 3, so I'm going to have 3x squared, and then 3 times negative 3x, and then 3 times 1. Okay, so evaluating this, I'm going to have x to the power of 5. So remember, when you are multiplying terms with the same base, you are adding the powers, so 3 plus 2 is 5. Next, I'm going to have negative 3x to the power of 4. So remember, when there's no power, the power is 1, so 3 plus 1 is 4. Then I have x cubed. Moving over to my 6x and x squared, I've got minus 6x to the power of 3. Negative 6 times negative 3 is going to be positive 18x squared, because I've got my two x's here, minus 6x plus 3x squared, and then I'm moving on to my 3 and negative 3, so negative 9x, and then plus 3 on the end. Okay, so let's collect our like terms. So starting with my x to the power of 5, which looks to be my highest power. There's no other x to the power of 5. Then I have an x to the power of 4. Again, it does not have any other like terms. Okay, now I have a few x to the power of 3's. So x to the power of 3 minus 6x to the power of 3 is going to be negative 5x to the power of 3. Then I have 2x squared, so plus 18x plus 3x is going to be 21x squared. And then my negative 6x minus 9x is negative 15x plus 3. Okay, now we have evaluated, we have no like terms left, so this is where we end for this question. Okay, moving down to equating coefficients. So in our next chapter of 6b, we are going to go through how to use long division to divide polynomials, but we can also find coefficients by equating coefficients using our knowledge that we already have. So this question gives you the polynomial p of x, and it tells you that it can also be written in this form, which is a partially factorized form. So it tells you that b, c, r are real numbers, and it wants you to find the values of b, c, and r. So starting with our polynomial of x cubed plus 3x squared plus 2x plus 1, it's telling you that it is equal to x minus 2 x squared plus bx plus c, and then a plus r on the end. Now we could also rewrite this. So if I was to do what I had done above with my p and q here, where I've multiplied all the terms by each other, I could say that x could be multiplied by x squared plus bx plus c, and then I could also have that negative 2 multiplying x squared plus bx plus c, because that's technically what we're doing. We're multiplying x by each one of these terms, and then we're multiplying negative 2 by each one of these terms, and then the r is separate on the end. So now that we have all these terms here, what I'm going to do is actually expand these brackets. So x times x squared is x cubed, and then I'm going to have x times bx, which is going to be bx squared, and then cx, x times c. Doing the same for the second bracket here, I have negative 2x squared minus 2bx, and then minus 2c plus r. Okay, so now I've ended up with this, and I can see a few like terms coming out. So I've got my x cubed here, which is going to just remain as x cubed. Looking at my next factors, I've got my 2x squared terms here. So what we can actually do now is we can factor out the x squared, and we have our coefficient of b minus 2. So b minus 2 as our coefficient to x squared. Then looking to just my x terms here, I have the cx and negative 2bx. So again, I'm going to factor out my c minus 2b x. And then now I'm left with my constant terms on the end, so the negative 2c plus r. Okay, so now we're getting to our equating coefficients portion. And we're going to start with the one that only has one variable in it, because as we can see here, I have my c minus 2b. I'm going to need to know one of them before I can attempt to look at this, and same with my constant term on the end. So I'm going to start with my first coefficient here with my b minus 2. Now looking at this, I'm going to equate it with the coefficient that I know is with x squared. So what I'm going to do is say that b minus 2 must be equal to 3. Solving for b by plussing 2 to both sides, I'm going to have that b is equal to 5. So that is one coefficient that I have now. Next, turning my attention to this c minus 2b, I'm going to say that it is equal to 2. Now I found b from before, so I'm going to say that I know that b is 5. So c minus 10 is equal to 2. Plussing 10 to the other side, I'm going to have that c is equal to 12. Next, turning my attention to the constant term at the end, I'm going to say that negative 2c plus r is equal to my constant term on the end, which is 1. Now again, I found c last time, so I can say that c is going to be 12. Sorry, my pen just died. Now I'm back. So we've made c is equal to 12. So negative 24 is equal, plus r is equal to 1. Plussing 24 to the other side, I have that r is equal to 25. So now we've equated all of our coefficients and we've found b, c, and r. Just lastly, just reviewing this a plus b squared rule that you would have been introduced to sometime in year 9. This is, remember, called a perfect square when we have it like this with our a plus b squared. And we would have used this rule as well when we did quadratics. But we actually can expand this rule to be a plus b to the power of n. And when we do have this general rule here, we call it an identity, which means it's going to be true for all of the numbers for a and b. Now you can have n to the power, n being the power of whatever you want it to be, but just expanding on this rule just a little bit for the purposes of this chapter, we have the rules here for a plus b to the power of 3 and a plus b to the power of 4. Now, it works the same way as the other rule where a is whatever this number is here, and then b is whatever the number is on the right, and you're just substituting it into your equation. And then as we can see, as the power gets higher, we have more terms coming out of that expansion. I don't have any examples of this. I'm just expecting that we all know how to use this identity now.